All righty. I think we are 3 past the hour here, so I'm gonna turn the music down and we can kind of officially get started. So I know folks are trickling in, but welcome. Super excited to have everybody today for our Presto Virtual Tech Talk, our June Virtual Tech Talk, where we have folks from the Hudi community talking more about Hudi and Presto. So before I get started, just a few housekeeping items. First, introduction. Hi, everyone. I'm Ali Leclerc. I'm the chair of the Presto Foundation Community Outreach Committee. So you'll probably, if you come to Presto events, you've probably seen me. If this is your first time, we hope you come to more and you'll continue seeing me, but I'm excited to have everybody here. So first, I would be remiss in my duties as chair of Presto community team to not mention that PrestoCon Day is coming up July 21st. It's a fully virtual event. It's an event for the community, by the community. We'll have the Hudi team here, there presenting along with a bunch of other speakers from Uber, Meta, ByteDance. You can see it here, free to register. Highly encourage you to do that and attend the sessions that you're interested in. I'll drop the link in the chat as well at the end, but that's coming up next month. So we're super excited about that for the community. So without further ado, really happy to introduce our two speakers today, Vinod and Ethan, both from the Apache Hudi community, as well as One House. And today they're going to be talking about how to optimize your table layout using a Hudi to unlock stellar, I love that, stellar Presto performance. And so with that, that's all I need to say. Oh, one other thing, questions. We love questions. We love this to be interactive. You can see we're actually in a Zoom meeting as opposed to a Zoom webinar. And that's because we'd love for you to ask your questions verbally if you're comfortable with that. If not, we also have the chat box, which I see is people are already using, which is awesome. Drop your questions there. I'm just going to speak for both of you, Vinod and Ethan. Interrupt them if you have a question. We love interactive sessions. And so ask questions, fire away, and we'll have time for that at the end. Okay, now without further ado, I'm going to pass things over to Ethan. Let me stop share. And Ethan, please take it away.
Yeah, thank you, Ali. So today, Vinod and I are going to share our experience on optimizing the table layout for Presto using Apache Hudi, and then we'll showcase the performance improvement. First, to introduce ourselves. So I'm Ethan, as Ali already mentioned. I'm a database engineer from One House. I'm also an Apache Hudi committer. Before I joined One House, I spent 4 years at Uber as a senior software engineer, working on a lot of stuff around data incremental processing for global data. Also, like improving the mobile networking performance for our global users in production.
All right. To just introduce myself and kick things off here. I'm Vinod. I'm currently founder CEO at One House, and I also serve as the PMC chair for Apache Hudi with the Apache Software Foundation. Before this, I spent 5 years right before this, I was at Confluent actually working on Kafka KSQL and Hudi happened at Uber, where I worked on a bunch of things, including data infra, networking. That's kind of like how I know Ethan. And before that, I was at LinkedIn working on our key value store at the time. And started my career at Oracle. So I have mostly done databases for a long time. Cool. To just kick off today's agenda, we'll start with an intro to Hudi, and we'll then talk about actually table layout optimization. This is not a topic which is widely covered in many talks that we've seen out there. So we'll try to cover some of the the theoretical underpinnings and sort of paint a broader picture of where things fit. And then we'll talk about Hudi clustering and how you can apply some of these techniques using Hudi clustering, and then show you what it does to your performance. And end with generally talking about the Hudi community, where things are headed, roadmap, and then we can break out into questions. All right. So quick recap. I think going back to even, I think it's important to understand how Hudi started because by and large, the problems that we saw at Uber back then when Uber was in hypergrowth mode, moving from a warehouse to a lake. And then the problem was, well, whether you have cloud storage or HDFS, it's an immutable storage system. And you need to really build, a database or transaction layer on top of it, right? That's how Hudi was born. So specifically, what we had was we were trying to ingest our trip database, and we were like bulk ingesting it like everybody else was doing at that time. And we had this, cost us like 120 terabytes of conversion from like our OLTP format to Parquet every 8 hours. And then what we would do is we'll, full recompute all these downstream tables again, big batch jobs, batch ETLs. And what we saw was we had extremely poor ingest performance, a lot of wasteful reading and writing and IO and compute spend. And then through all of this, right, anything here can fail. These are like very large jobs that can fail. And then there is no concurrency control, no like guarantees of atomicity, rollbacks, nothing really, right? So this is how Hudi really started. As you can imagine, it's a pretty much more complex kind of like problem space than, let's say, purely table formats, right? Which is, okay, let's optimize for, metadata access to a table. So we actually started with the entire feature set of, the database problems of updates and incrementals and everything. So when we thought about it, what we basically realized was this actually wasn't not like a new problem, right? Like all databases pretty much solve this problem. It's just that we need to now figure out a way to implement this in a way that fits data lakes. So essentially what we came out with was, okay, if we build a system where it can absorb updates or delete records, you can update a table and then query a snapshot consistently, right? No dirty data. Things are either committed or not. And also be able to do point in time queries. That way we can, if something is off, you can go back in time and figure out actually when it was actually correct, the table state was correct, and then you can replay and rewind, do these things. So, and then we also needed, since, it's not enough that we solve the ingest problem, right? Going back to the previous slide, we also need to incrementalize the ETLs downstream as well. So that led us to, build incremental changes, which is something that, Hudi is the only project out there in open source that has these functionalities to date. And again, while all this is going on, this has become a database problem. Every database has daemons and internal processes that manage the database, right? So we implemented a suite of services, what we call table services, which all work together and manage the table. So this was the core idea. And when we called it a transactional data lake at that point, it's kind of like a nerdy terminology, not as catchy as, test well in markets like Lakehouse, but it's a similar idea, right? And I think at that time introduced, hey, we don't want to build, at that time, things like Kudu and other things were coming up, but we were pretty cognizant about not introducing like a server-based layer. So we decided to build a serverless transaction layer where you just take cloud storage, you already had files. Let's add some metadata transaction log, and then expose some APIs and make all the writers and queries kind of recognize them, right? This is pretty innovative and kind of like, pretty new actually at that time. And we did it, even the very first version of Hudi, we had to make it work across Hive, Spark, Presto at that time inside Uber. And we introduced two like storage types, which you can see it's even borrowed pretty heavily outside. One, copy and write, and merge and read. We'll look in quickly into what they mean. And sort of like, once we had all this, the resulting architecture was, well, we had a database abstraction now. So we can use fast upserts. We have we build different kind of indexing schemes in Hudi. If you're a Hudi user, you may be aware of this already. And you can incrementally build ingest tables. If I look back at the 5 years of doing this, I can confidently say most people today don't even think about doing the batch bulk load ingest, right? And the second part, which I think, there was a talk yesterday from Uber where Uber builds most of these core warehousing tables in an incremental fashion, where we actually process only the incremental changes every few minutes and then run it. This, I would say, is not as mainstream as it can be today. And this is like where a lot of our attention and work is also going towards. So to quickly touch upon sort of Hudi's different table types, right? So copy on write is very simple. Essentially, so let's zoom out a little bit. So the problem we want to solve is, okay, we have a table and a bunch of Parquet files and few records are changed, right? So how do we, like, what are different ways that we can deal with it? The copy on write and the merge and read tables deal with both of them very differently. So a copy and write, what you can see here is, let's say you insert A, B, C, D, E, Hudi organizes it into 3 files, let's say. And then if we can query snapshots or incremental queries, and then you'll get the same thing because it's just the one commit. But when you update A to A prime and D to D prime, it just creates a copy of the files that are actually affected. So you can see that it doesn't touch file 3, but it actually makes a copy of file 1 and file 2. It copies over B while it changes A to A prime. And now if you query the snapshot at commit time 1, what you get is, like the latest values for each of these records, which is A prime D, B, A prime B, C, B prime E. And then when you do an incremental query, since Hudi tracks record level, commit times, and we know at A prime, we stamp it with the commit time at which it gets updated. So we can actually easily extract A prime and D prime and pass it downstream to another ETL process. And similarly,
Vinod, one question. What if, at that time, record E was deleted in the next subsequent, so what should be the output of incremental query?
Yeah, so so today, I think we encourage users to do soft deletes, which is essentially you retain the key and you null out the other fields, right? Then you will get, essentially it's like an update. You'll get it in the incremental query as well. There is a new CDC format that is being defined right now, which will also handle hard deletes. And just to give you the context for why we did that is because there are, let's take the Uber example. You guys all know about delete Uber and all that stuff, right? So if somebody deleted their account, or even for GDPR, somebody deletes their Uber account, then the trip did happen, right? They actually had trips from before. And so essentially we want to null out all the sensitive data, or personally identify, all of that is deleted. But for analytics, right? Like, okay, the fact that this trip happened, like we collected that fare, those things are important, right? So I think for most scenarios, so far, even in the community, when we give, like, can I approach this conversation, people usually are like happy with a soft delete and you can then get it in our incremental query as well.
Perfect, thank you.
Sweet. All right, so as you can imagine, copy and write has very high update costs, right? While for reads, it's pretty simple. It's almost like reading another Parquet table, while all of this is internally managed under hoods. Merge and read is like a lot more flexible, right? It needs a lot more, I would say, operational jobs, as well as like, more things to be done operationally. There are more moving parts. The core idea again is, now, everything is the same till we do the first insert. But when we want to update A to A prime and D to D prime, we don't actually rewrite the entire Parquet file. You can imagine this, right? Most scenarios, you're probably even updating just one column. And then you have like 100 MB Parquet file where like, small set of, one rows, one column or something changes. Then you don't want to rewrite the whole thing over and over again. What we do is we queue up all these updates into like a delta log. Ironically, Hudi has delta logs. What happens is eventually a compaction process runs where it merges the base file and these update logs together to produce a new kind of like base file. And until then, when you do a snapshot query, it merges the base and the log file on the fly. And this is done in a columnar way. Like we send projections to both the log and the base, and we merge things out by key. An incremental query, again, it's pretty simple, as you can see, because the log already has, it's an ordered log. So you can read through the log and get new changes from time t. And we also support another thing called read optimized query, which is kind of actually can be used in a very practical way. It does not have very good, consistency guarantees. These consistency guarantees depends on how you compact the table. But like a real world use case or something like, sorry, I'm getting some, is there a question or somebody else's mic? Okay, all right, we'll go on. So real world usage for something like this would be, let's take, again, like the same Uber example, you're getting new trips flowing into the last few partitions, like date partitions, while somebody's like deleting, scrubbing old data on an upstream database, right? The upstream database is super happy because, it's a OLTP database, it can take random updates. But that kind of workload, what will happen for copy on write is that it will just increase the number of Parquet files you're versioning, right? So instead, what you can do is you can use a merge and read. You can choose to compact the latest partitions completely, right? And if most of your dashboards are hitting last 7 days, last month, or things like that, then you get like with read optimized query, it only queries the base files. So you get columnar performance and the latest data, while you can run a compaction every few hours or once a day or something like that. Then you bring the table back to the consistent state. So that is a practical use for read optimized query. The main key point is Hudi provides all these different queries on top of the same sort of like physical data set. These are like logical views of the same data underneath. Cool. So quickly picking up speed a little bit here. So the table structure, if you peek inside a Hudi table, here's what you'll find, right? You'll find that there is a bunch of files which are all have the same UUID prefix. So this is what we call as a file group. And we group files into a file group. The file group is the smallest unit for concurrency control, updates, and that's what the index tracks. Everything is, that's a central kind of like data model, like data object inside Hudi. And when you write some records, it essentially writes for each file group, as you can imagine in copy and write, going back here, right? All of file one underscore T0, T1 underscore T2, all these things that start with file one, they all belong to the file group one. And then what we call a slice is every version of a base file, right? So updates generally write records to the latest file slice, and then we commit to a event log or a commit log that we have. Then we have an internal metadata table that holds other auxiliary indexing and multi-model indexing and column stats, file listing, all these kinds of like metadata around it. And the queries can read the metadata from the .hudi folders and then plan the query and then go to read the data. I'll skip over this for a little bit, but just to close this out, Hudi, just to give you a brief tour of what Hudi as a project today offers. On top of like lake storage and open formats that we have a table format component, which is kind of like a integral, but one portion of the functionality that actually Hudi offers. It stores schema, file listing, stats, schema evolution, these sort of things that you will kind of expect to find. We also in addition to that, we have a rich set of table services, things that can reclaim storage, or for merge and read, compact log and base files, things that cluster that we'll see in more detail, build indexes, size files, anything and everything that you need to have like well-optimized tables or in table services. And we have support a bunch of different indexes for, at this point, mostly, good update performance, but we are expanding these indexes. So all our work recently around multi-model indexes and everything feeds into kind of generalizing these for joins and stream joins and these kinds of things to even expose this to the query side. And for the Presto community, that's where the recently added Presto connector is going to be like super awesome vehicle for us to sort of start exposing these indexes to Presto queries as well. Concurrency control, we provide multiple, not just OCC, but MVCC, non-blocking concurrency control. And for all these table services, right, you don't have to go to Airflow and then, figure out how to schedule all this or something. Hudi has a runtime which can automatically schedule cleaning compaction. If it fails, it'll retry, it'll manage. When you schedule compaction, it knows that clustering is already scheduled. These things are aware of each other. So this entire orchestration scheduling layer is also provided as part of Hudi. And
yes,
I think yeah. Sorry, any question? Okay. All right, so we are investing on 2 new components. I think the meta server is much further along than the cache, which will, I think we believe will significantly improve the query performance on top of the kind of storage organization that we have. This is what we call a fundamental transactional database layer inside Hudi. Then we expose this out to all these different query engines. And we also have a rich set of platform services inside Hudi where you can do ingest and admin CLI. There's a sync service which can sync your tables, keep the schema and everything in sync, and data quality checkers. There's actually a pretty significant amount of platform services that the community has contributed over the last few years.
A quick question in just a slide.
Sure.
Can you call out which of these features are already in the latest version and which are coming in 1.0 and in the future?
Yeah, I think the ones that are dotted are all like being built. The ones with the dotted boxes, right? Those are all being built. And overall, maybe, I think even the Lucene one, there's a PR up now, I think. And then the hash-based one, there's a PR up. And then like Uber's basically been testing it with like a 13 terabyte like index or something like that. So it's all there. We need to take those, bake it in, generally test it, like certify it for the open source community. But if I haven't marked something out, there's either a PR out or it's, already there.
It's under development. Got it. Thank you.
Cool.
Hey, Vinod, we also have a few coming in through the chat. So I'm just going to do those now, if that's okay. So one is, how is the latency incremental query on copy on write versus merge on read?
Yeah, great question. So obviously, for incremental queries, for merge on read, it's a sequential scan, right? It's going to just like read fewer objects. So it's going to be like a little bit more faster. But even for copy on write, since we track, if you look at Hudi tables, they have a _Hudi commit time, commit sequence number. So we actually track when a record was actually changed. And when we do the incremental query, we actually push projections into Parquet. So I would say that the incremental query on copy on write will be a tad slower than on merge on read. But let's say you have only 1 record, 2 records changing in a given Parquet file, you won't see that much of a difference. I can go deeper, but high level, it depends on how your changes spread across Parquet pages and row groups, because Parquet has to read the page. That's the smallest unit that it can read. So if you dirty 1 record every page, yeah, it'll read the entire file.
Great. And then another one, is Avro already supported for data files, not talking about log files?
Actually, no, I don't think that has come up. That'll be like interesting to understand. We have ORC supported for base files. We have now H file supported for base file, and the log can actually contain Parquet now. But this particular thing hasn't come up as much. Most people, I'm happy to, please raise a Jira and happy to see how we can accommodate that if that's what you need.
Cool. All right, I think we can keep going.
Vinod, so I have one more question. So like talking about the data quality thing that you mentioned as part of the platform services. So yeah. I know of the dedupe job that we have. So are we having any other support for data quality apart from that as well?
Yes, I think we have a SQL-based checker. I think there is, so if you go to the site and look at, let me quickly grab you the actual thing. There are 3-4 ones where you can essentially run a SQL query before you commit into the table itself. That way, let's say you the batch of data invalidates some constraints for you, you can reject, not commit. I think it is called I think services data quality. If you go to the docs, you'll see that there's like three of them, and you can write your own and plug it in. You can write it a Java class and add it in.
Okay, yeah, thank you.
All right, sweet. All right, I think I took up more time, so I want to make sure Ethan has enough time to go over the core meat of today's talk. Take it away, Ethan.
Cool. Sounds good. So yeah, next I'm going to talk about like how this table layout optimization is and why you can unlock the query performance improvements. So if we look at this slide, so here's the life of our query. So from a burst view, so it takes like several phases from the query to the end results. So it starts from first fetching the metadata and then plan the query based on that. After that, so the engine reads the input tables and try to do SQL transformations to get the actual results. So there are different optimizations that goes into the different phases. For example, the table formats, including like file listing, column stats, with the meta store that can enable the efficient meta fetching. And there are kind of different SQL optimizers like using cost or heuristics to improve the quality of plans. Is there a question? Okay, so there's also like other like engine specific improvements to speed up the SQL, like vectorized reading, serialization, shuffle algorithm, etc. So for the focus of this talk, we are more interested in how to actually read query bytes for the input from the input table. So if we can do this right, that can actually result in orders of magnitude speed up. And we'll also showcase this later. So to dive deeper, actually there are already general techniques in databases to kind of reduce the number of bytes for reading. So one of them is using the index. So index is like the pointers towards the specific data one wants to look for. For example, this is like a book index. If I want to look for a specific keyword, I can look at the index at the end of the book, find the page number, and then I can directly go to that page to find the information I want. So similarly here, like this index table stores the pointers to the specific data or entries that users want to query. So this is very helpful for like selective queries like this needle in a haystack type of queries. So even in Hudi, we already support different indexes like Bloom filters to improve like the lookup time. So indexes actually reduce the amount of data to read. So how about we actually skip the actual reading for some part of the data, actually not reading from the storage. So that's how caching comes into place. It actually limits the access to the storage for most of the cases if the same set of data is being accessed, so that the caches can actually provide the data without actually reading from the actual storage. Even better, beyond that, if we do want to read data from the storage, we can still do some kind of optimizations like storage layout to control how data is actually organized. So one simple example is that these bucketing techniques. So for example, for all of the records, we can use the hash to get like one number so that all of these records are bucketed into different segments. So whenever we want to query some of the data, we can get the bucket number, and then we can directly read that bucket without having to scan off the other data. A more advanced technique than bucketing is the classing. So this, so if you see this naming, it's actually similar to, for example, the machine learning k-means clustering. So the essential idea here is that we want to actually put the data with same or similar column values together. So that's how it's named clustering. Then, as you see on this slide, if the table is not clustered for the same column, for example, if this is like a trip table from Uber, and then each each record is color coded by the city. So if each file has odd records from different cities, it's scattered over the place. Then if you want to read read data from one city, then you have to scan all of the files. But if we cluster based on city, so all of the data from the same city is going to the same file or same set of files. For example, like on the right side for the green one, it only shows up in like file 6 and 9. So in this way, instead of scanning all the files, all the 9 files, then we can reduce the number of files to read, like down to 2, for example. So so this slide shows some more like details of how these clustering can help the query planning. So on the top side, we have this unclustered table. We have like for example, we have 10K Parquet files in the storage. Then the query will first, and then we have this select star from table where session ID equals 1, 2, 3. So let's say if it's unclustered, then this session ID is scattered over all of the 10K files. So in the query plan, then it has to read all the 10K files and then return the result after the filtering. But now let's say if we cluster based on the session ID column, now even if we have 10K files in the storage, and then maybe after clustering, it only has like fewer files, like maybe 1K files, we can still reduce the number of files to read. So let's say this session ID 1, 2, 3 only appears in one of the files based on like the stats. Then this after predicate push down, we only need to read this one file. So you can see here that it provides like some 10 or even 100x improvement on the number of data scanned. So this is pretty amazing. So so you can see that if we're talking about one column, it's easier, but usually the data is multidimensional. So how to tackle this? One of the straightforward ways is that we have all these different fields, right? We can sort it linearly, one by one. So you can see on the right side, let's say we have like 6 fields. We first sort by field 1, and then by field 2, and then by field 3. So in this case, this is actually very good for queries with like hierarchical predicates. Let's say we can use F1 as predicate, or F1 plus F2 as predicates, or even the first 3 columns as the predicates. Then data are actually collocated in the files. So these are pretty good. But one issue, as you can also see, that if we just look at one of the column, for example, if we look at column 3 or field 3, the data is actually scattered all over the places. So if you just have the predicate like this, the efficiency is not actually that good. And the effectiveness decreases from the left to the right as it goes. So that's how the advanced space curves try to solve this problem. The basic idea is that still we have these multiple columns. We want to have some ordering so that we can still provide locality, but not too much index on one of the column, like the first one or second one. So then the idea is that we map these multiple dimensions to a single dimension with some space curves in like even 2D, 3D, or high dimensions. So these space curves are not something like new or something reinvent. There are like a dozen exist in the literature, like over the few decades from like the math community. So there are two major space curves that come into play. One is the z-order curves. So on the right side, you can see like this is how the curve looks like. The reason why it's called Z order, because the curve looks like a lot more different Z's. So instead of going all the way from left to right and then left to right using the linear sorting, it uses like this kind of binary representation of points and then trying to interleave the values so that you can see on the top left corner, these data are co-located. So it provides better locality. Similarly, it moves on to the next block on the right and then the block on the bottom left. So these resulting in like the order depends on all the fields. That's how the order curve works. Another more advanced curve is called Hilbert curve. So this one, instead of using like kind of Z patterns, it uses more like a perpendicular segments inside this space. So based on like the research, it provides better ordering properties for really high dimensions, like for example, four or even 5 or even 10 columns. However, it's more expensive to build compared to like the simpler Z-order curves. But you can see that there are different options to choose for this multi-dimensional ordering. All right, so if all of these seem very complex to you guys, there's some very great news. Let's go to the next.
I think there's one question, Ethan. Maybe we can answer this in line. After Hudi clustering is completed, I guess any new update might be declustering in the files, maybe due to size. Is my guess correct? Correct. Yeah. I think technically you're right. You could be, let's say you change the dimension value, it could decluster, right? And then where there's some pending ongoing work, I think this is Jira for this too, is to kind of, you have to build a sampler sort of like thing and then understand the stats and figure out what part of the table is fully clustered. It means, it's like converging and not converging. Right now, the clustering scheduling is, if you look at the parameters for scheduling, it's kind of like assuming that the dimensions are mostly same. Most of the cases, until the data is completely bad, the dimensions usually are the same. Mostly the fact values is what gets updated. So, and most people cluster by dimensions. So we've not considered this very highly so far, but you are right. It's a great question, actually.
Yeah, so adding to Vinod's points, so if new data comes in, then it may add to like existing files or new files. So that may not conform to the existing order. So this clustering has to be scheduled like periodically so that the data is in like a better layout.
Yeah, the queries will still work fine though. It's just that it'll be like inefficient until we fix that.
Right.
Another question. So can the clustering job be a schedule only on the Spark job that's currently running a Hudi streaming ingest? Meaning pausing capturing the resources that's doing the ingest can actually slow down the ingest job. So can this be configured as schedule only, meaning you basically write a cluster file in the Hudi timeline, and an offline another cluster will actually pick it up. Yeah.
I think we have a slide around this. All this can be done. There's a slide around this. We'll just get into later. Okay.
Right.
And there's I think there's two other. Once data has been sorted based on some files, is it indexed by Hudi to track which fields can be found in which files? Yes, clustering will also update the index component. And this is why, it becomes pretty clear that this is what Hudi is like kind of trying to solve is a database problem. That's why we need clustering to be aware of index and indexing to be kind of like, all these things are very interrelated. Felix's question, any improvements done to clustering of large partitions? Yes, I think 0.11, there is, even 0.11.1, there's been like new improvements to clustering speed. And Ethan can actually share, as he talks about this number, I think we can at least give you some sense of like till what we've been testing with.
Right. Right, sounds good. So let's move on to the Hudi clustering. So as I mentioned, like these storage layout may seem very complex, but Hudi already makes it pretty easy for you. So so we have these Hudi clustering. So the goal here is that we want to optimize the data layout alongside the ingestion. So there are two problems that we observe here. So the first is that if we really want to do this like incremental ETL to enable like fast ingestion, that means usually it could result in smaller file sizes, which is actually not very good for query performance. The second problem is that the data locality that is actually more efficient for query could be different from ingestion order. So usually the data comes in by timestamp, let's say this trips table. But for the query, we may want to query data for a specific country or city. Actually, that's different from time. So the order is different. So how Hudi clustering is trying to solve here is that it tries to do auto sizing and data organization without any compromisation on the ingestion. So that ingestion can go on while clustering can run separately. So that's how, so in Hudi, like we use the table service to provide this self-managed clustering so the user doesn't have to worry about all of the internals. So there are two steps. The first is that the writer schedules the clustering plan. So it first identifies the target data or the file slices for clustering, and then generate a plan in the timeline. So later on, either the same writer or another async job can pick up the plan and then execute with a pluggable strategy. So for example, for reorganizing the data, you can choose to use linear sorting or these different space curves, including Z-order or Hilbert. So what's even better is that the Hudi clustering provides this transaction property, so that if the clustering is ongoing, it will not be visible to like query side or even read side. And once it's done, the replace commit is put into the timeline so that the new table storage layout is visible. Cool. So here, I think going back also to answering the question about like how we use, how we run like clustering in different modes. So clustering can be scheduled and run inline or async. So we actually provide different like multiple modes so for the user to choose. So for like a very relaxed SOA, like the clustering can be run inline, like the first one. After ingestion batch plan, you can first do the clustering, and then like after that, it continues with the next ingestion. It can also be async. So we provide this async clustering service in Hudi data streamer. So it's scheduled to run async automatically. Similarly for Spark structure streaming, that's the same model. Or for some tables, the clustering can take a lot of compute resources, as you mentioned. So then the ingestion writer will just do the scheduling. There can be another independent Hudi clustering job scheduled by user to actually execute the clustering independently. That does not actually affect ingestion. Or even better, you can manually run the clustering using Hudi CLI. That's another flexibility we provide.
I think there are quite a few questions, Ethan, here. I think good to clarify. I think going back to Pradeep's question, which is, yeah, there is like, a separate job that you can run, and you can have it whichever way, even within the Hudi Delta streamer or structured streaming. you can configure Spark pools to give it, a minimum amount of resources for your ingest. And that's actually how we even deploy these things for OneHouse. And it takes a little bit more tuning in Spark, but you get like one job. That's it, right? That job is doing everything for you. That's nice in one way if you don't want to run a separate scheduler. Second question is there any impact on read performance while clustering is in progress? So clustering is atomic. It will move the table from a non-clustered to a clustered state. So in terms of read performance, going back to our little diagram there will be a little bit of extra planning work to do, but it doesn't affect any of the other stages, like the actual reading, execution, the IO path is not affected. It's like very minimal extra work to recognize an in-flight clustering and ignore some of these files or something. That's pretty much it. It's pretty lightweight. Clustering is a batch process, and if you use Delta Streamer continuous mode or Spark streaming, it is triggered continuously for you. It's just like the Spark micro batch, mini batch concept. Some runtime will constantly keep evaluating. After every write, it will evaluate whether we need to cluster the table based on the configurations that you have. And then if you feel like, I want to cluster, then it's going to take the data and cluster it. I think the Spark pooling strategy, I think most of the docs isn't just the plain Spark docs. We can follow up more on the community and we can update, if you can give us a little bit more pointers, we can actually update our side docs as well. And let's see, is this starting from point 11.x? I don't know what this is. Harsha, can you clarify that?
Yeah, so the offline mode where you can schedule it and offload it to a different Spark cluster.
No, it's always been like this. It's been like a while. I think we probably rewrote all the docs recently, maybe. You can still see my screen, right? Okay.
Yes.
All right. Does pending clustering jobs have any impact on Delta commits? Yes. So right now, the one thing that we don't handle, we handle by failing either clustering or ingest is if you have a concurrent update. If you have a concurrent update for something that is being clustered, that's so Hudi supports concurrently running compaction and writing, for example. But for clustering, we don't have that implemented. So we'll either fail the write or fail clustering, depending on what you need to do. And that's where I think we need a log service, and then it's safe.
Can the user prefer which one to fail?
Can user, yeah, there is a strategy for reject and do this. I think one of them is safe regardless. Another is only safe if you have a locking service. So
we'll check the logs. We'll check the docs. Thanks.
If it's atomic, then will you lose progress if there are failures? Are you planning to stage your clustering progress? Okay, yeah. So it's a great question. So I think we want to move towards a model where instead of building that, let's use so now we added the column stats index, and we have a pretty good capability to store actually large amounts of stats as well, right? Because it's an internal Hudi table. So I think a good point for a thing would be for us to run clustering itself in smaller batches. That way we just there's more clustering, but each of them are atomic. And then, that way we can avoid a big clustering job failing and then eating up resources. I think that's your concern. I think that also ties into an earlier question around, can it happen continuously, right? Cool. I think we answered all of them. All right. Cool. Awesome questions, folks. This is super awesome. Cool. Yeah, go for it. Okay.
Yeah, sounds good. Yeah, me continue explaining how this table layout optimization can be used in Presto. So to give like some background on the Hudi Presto integration. So Hudi is already supported via Hive and the new Hudi connector, which is merged recently on master. So I'll quickly go through like what's supported. So for Hive connector, suppose the snapshot and optimized queries are supported for COW and MR table. And Presto is recognizing Hudi file layouts through like the native integration. And we have we use the Hudi table metadata to enable the file listing so that Presto can actually know what files should be read. For the new Hudi connector, which is merged on master recently, we support the snapshot query on COW and the read optimized query on merge on read. So this new connector opens up more optimization opportunities. For example, the recently incorporated data skipping in our latest releases, as well as the multi-model indexes, where we can include more these advanced indices. So as I already talked before, so these the optimized storage layout actually improves the data, how data is organized in the storage in Hudi tables. So that affects how Parquet table is written. So this is already readily available for Presto without any kind of like new integration point. All right, cool. So next I'll talk about how the table layout optimization in Hudi leveraging clustering improves like the query planning and reducing the number of bytes read. So I'll first talk about our experiment setup. So we use the GitHub archive dataset. We pick like 12 months data in this time range. So in total, there's like around nearly like 500 gigabytes of data in Parquet. So around 1 billion records. So we specifically look at some of the columns cardinality, for example, for these. So before talking about this, to give a quick overview of what this GitHub archive dataset is. So it stores like different events around like repo activities, for example, the new pull request, the issue comment. So each activity is represented by one event, which is one record in this table. So if you look at the cardinality, so this type meaning like what is the type of event? For example, pull request, issue comment, or even PR merged. And the repo ID represents how many repos in the GitHub. There are like around 65 million of repos. And we also look at like the hour update. So to see like if you want to look at like particular time range. So to measure like the storage layout optimization, we write Hudi tables, the COW tables, partitioned by year and months. We use bulk inserts and followed by clustering if we want to enable the storage layout optimization. We pick 3 columns for sorting or ordering, the repo ID, type, and hour of date. So we compare 3 different strategies, no clustering, linear sorting, and Z-ordering. So we leveraged our Presto setup on EKS with the latest snapshot of Presto. So we have 1 coordinator and 4 workers, each one having like 15 vCPUs and more than 100 gigabytes of memory. So here are the setup we use. So in the next slide, here I gave like an example of how we configure Hudi clustering. So it's pretty simple, and this is also available in our clustering docs. So first, we need to enable the inline clustering in this setup, and then control the clustering frequency. Then we basically configure the sorting columns and different file sizes and the strategy we want to use. Cool. So next, let's talk about the actual numbers. So we look at 2 kind of business questions. One is how many activities for a particular repo, and the second is how many issue comments for this time span. So if you look at the actual query, we have 2 different predicates. One is based on the repo ID, the other is based on the type. So if you recall, the sorting columns are first is the repo ID, then the type, and then the hour of day. So we compare the number of rows scanned for these two queries. So if there's no clustering, basically all of the data have to be scanned. That's the blue bar. And then for the linear sorting, if we look at the first query using the first column as the predicate, the actual data scan is pretty low because it's already organized towards that. But if we use the second column as predicate, since it's scattered around the places I showed before, it's almost similar to no clustering. And if we compare the Z ordering with these two, it tries to balance these two, sits in the middle. So it somehow is a little bit worse than the linear sorting for Q1, but it's much better than Q2. So it balances like the predicates for all of the columns instead of over-indexing for one. So the key takeaway here is that so linear sorting suits better for hierarchical data. So you want to have multiple columns for predicates. And Z-ordering balances the quality for multi-dimensional data. So these provides like a balance between these two. So it really depends on what are the queries and the predicates to select the best the layout strategy. Cool. So that's about how storage layout can improve the performance. So back to Renaud to talk about the Hudi community.
All right. Yeah, we can dive into this more, but thanks for the awesome presentation, Nathan. I'll go quick here. Generally, status of the community, Hudi is actually doing really good, and we there's so many very large enterprises who are building, tons and tons of tables and very large data lakes using Hudi, as you can see. And we have like a really good momentum starting in 2021, and picking up even more steam as we go through this year. And that's the other thing. The thing that I want to because a lot of people come and talk to me about whether we are the Hudi company. We're not the Hudi company. OneHouse, is another big power user for Hudi. We are firmly committed to Hudi, and we will, we have like our own Hudi development team. But by and large, the community is still super diverse. We have, I think, 14 PMC, something like that. And we have like 3 in OneHouse. So it's like a pretty diverse community. So if you're interested in becoming a committer, working towards a PMC membership, all those things, please engage with the community using the official channels, and we'll be happy to have more contributors and more people part of the community. And yeah, generally how we operate is that if you're a developer, you can propose new RFCs. You can go look at existing RFCs on GitHub. You can look at PRs with the label RFCs, and you can see what large efforts are going on and try to, see if you want to take part in one of them. There's devlist discussions, Jiras. We try to do monthly minor releases and then quarterly major ones. That's what we try to do. And we'll get it's still a pretty hard release to coordinate because it's super distributed. So many different organizations have to come together for a single release. But we are investing a lot in, testing infrastructure, automated release qualification, things like that. So we are really striving towards hitting that goal. And for users, there is a weekly community on-call person who can answer questions on Slack. If you've seen our Slack channel, there's weekly office hours. There is a monthly community sync. So if you have a cool Hudi use case that you want to present, just ping us or ping Sudha on the Hudi Slack channel. And I'm not sure if you have a lot of time to go over the entire roadmap, but I try to highlight a few things here that are very relevant to this crowd. So overall, right now, post 0.11, we had a pretty large release. So we are focused on stabilizing 0.11 performance, reliability, usability, a lot of low-hanging fruits like I don't want to have a key, I mean, some of these things we've taken a more opinionated view in the past based on kind of like practical experience running these things at large scale. But we do realize that, kind of like we try like loosening these things up and generalizing some of these things. So we're doing a lot of things around that. And we have the Presto connector actually landed already. So which sets up really well for actually bringing our Spark integration is pretty fully featured right now. But with the Presto connector landing, I think we'll do like a lot more work towards making Presto completely, full featured, and you can expect more work around that. We don't know extend again Arc. We have it waiting for Spark. We want to extend it to all engines. There's a bunch of stuff that works for Spark today that doesn't really, it's not exposed out to engines like Presto. So a lot of the work, I think in the next quarters you will see is all these different integrations. And of course, towards our 1.0, there are like big items like caching, meta server. There are actually like the team at ByteDance, they're actually working on the meta server. They're working on a service for table service orchestration. Actually, this year, Hudi is gaining new server components actually. So getting again all of those integrated under Presto queries. There's like a lot of interesting, very cool work that's scheduled out here in the roadmap. So we're always looking for contributors. If you want to be a part of any of these efforts, just ping on the dev list. We'll help you discover where epics are and kind of pair you up with the right committer or the shepherd to kind of like be part of those efforts. Yeah. Quickly touching upon the meta server. Why do we need a meta server? Interesting fact is Hudi actually already has a meta server. If you run the Hudi Spark writer, there's actually a meta server that runs on a Spark driver. It serves out all the RPCs and acts as a layer in front of even going to cloud storage. We are thinking, see, the thing is, if you think about it, we right now in the lake landscape, right? Like people just think about formats and table formats. And that's like in my opinion, a pretty limited, narrow vision, because all that table format does, as we saw before, is remove bottlenecks in query performance. These bottlenecks are already removed for warehouses. Most warehouses have a built-in metadata layer, which is highly performant, which can help fetch stable metadata, right? So I think we have to move beyond that. To move beyond that and run like mission critical performance, things like very fast meta servers and caching layers are actually required to actually bring like we actually see that these two components are needed to actually complete the lakehouse architecture. And this is a small benchmark that we run. You can see that if you directly list S3 versus using our internal metadata table, sure, there's an improvement, but look at the numbers you get from our timeline server, right? Which is like, sub like millisecond, like kind of, response rates that you can get out of that. So we are building that. And actually this part is much closer than the cache. The cache, I think the Elixir folks are interested in writing this. We are also looking for, we have a strawman design. We are also looking for people to run. So if you're really excited by this, ping us, and we can take Presto Hudi and like make the cache work in between the Hudi layer as well. And you can find us on Twitter, GitHub, on Slack. You can go to the site and sign up for our community things. And thank you so much for being here today and asking all these amazing questions.
Awesome. What a great presentation. Thank you both, Vinod and Ethan. I think we got a lot of questions along the way, and we are a few minutes past the hour. So thanks everybody who stuck around with us to the end. We hope you found it informative. So we do these every month. We do a Presto virtual meetup every month with different folks from the ecosystem and the community. I posted it in this chat. We also have PrestoCon Day coming up next month, where Vinod and I think somebody else from the Hudi community will be presenting another great session. And then we have a bunch of other Presto sessions going on. It's free, it's fully virtual. Register. We hope to see you there. And with that, I think that's it. We did get a question. The recording will get posted. We have the Presto Foundation YouTube channel. we'll put the video there, and then we can also post the link to the video as well as the slides in the meetup. So make sure you join the Presto DB meetup group, which is where we'll post it. With that,
right.
Thank you both, Vinod and Ethan. It was great to have you, and we'll see everybody next month.
All right. Bye-bye.
Thank you, everyone. Bye.